Hello, welcome to Advanced Composites. Today is the start of the 8th week of this course, and over this week we will continue our discussion in the context of solutions for these partial differential equations which were generated to represent the equilibrium of laminated composite plates. Well, last week we have focused exclusively on semi-infinite plates and their solutions, and at the close of the last week we started touching upon the issue of thermal stresses and thermal strains, because these types of stresses and strains are very important, especially in context of laminated composite plates, because they are associated with the manufacturing of these plates. So, in that context we had developed equations of equilibrium and also modified ABD relations for these types of plates which have inbuilt thermal stresses and strains. And then we started to solve a particular problem related to semi-infinite plates, so that it helps us understand the issues at hand better in context of thermal stresses. So, the problem which we were discussing was this one, and here we have an semi-infinitely long beam. The dimension in the length direction is A, the dimension in the other direction, that is its width, is B, and we have assumed that A is extremely large compared to B, and the plate is free to move. So, it is not constrained on either of the edges. So, because it is free to move, the boundary conditions associated with such a plate are given here, that on both the edges x is equal to plus minus A over 2, the external value of Nx, that is Nx plus or Nx minus, is 0, also Nxy and Nx plus is 0, and also because it is not seeing any external moments or shear forces. So, Mx is 0 and also Qs effective is 0. So, for these boundary conditions then we proceeded to solve the governing differential equations. From the first differential equation, which represents equilibrium of forces in the x direction, we got Nx is equal to C1 equals 0. From the second governing equation, we got Nxy equals C2 equals 0. So, these are the two governing integrations of the first two governing equations, and from the third governing differential equation, which represents equilibrium of forces in z direction as well as equilibrium of moments along x and y axis, we got d2 mx over dx square equals 0, and when we integrate that we got mx equals c3x plus c4, and because mx is equal to 0 on both the edges of the plate at x is equal to plus minus 2 plus minus a over 2, the values of integration constants C3 and C4, they turn out to be 0. So, mx is equal to 0. So, in overall sense Nx equals 0, Nxy equals 0 and mx equals 0, and that makes sense also, because the plate which we are discussing is not seeing any external forces and it is free to move. So, we should not expect any internal forces and moments in the plate. So, once these equilibrium equations were integrated, then we proceeded to linking these values of Nx, Nxy, Mx and so on and so forth with mid-plane strains and curvatures, and through mid-plane strains and mid-plane curvatures to mid-plane displacements u, v and w naught. So, what we had done in the last class was that we integrated the we stated that Nx equals a11 du naught over dx minus b11 dw over dx square minus nxt hat times delta t equals C1. Similarly, we also developed an expression for Ny and Nxy, and from the second equation, which is this one, we said that from the third equation for Nxy, we said we came up with an expression that V naught equals C3 over A66, and that equals to be 0. and then we were working on the fourth equation for mx. So, that states mx equals b11 du naught over dx minus d11 dw second derivative of w with respect to x minus mt in the x direction hat times delta t. And now what we will do is we will write down the other two relations for mxy and my. So, my equals minus d12 d2 w naught over dx square, because why is that? Because all the b associate terms for the relation of my, they involve what? b12 which is 0, b16 which is 0 and b66 which is 0. So, b terms do not come into the picture, and for my the d terms associated are d12, so that is non-zero, and so is d2w over dx square, and then the next term would be d22 times curvature in y direction which is 0 because the plate is semi infinitely long in x direction, and the third term will be d16 times kxy. So, d16 is 0. So, this is the only term which is left, and of course, there is a temperature related term. So, that is my hat T times delta T, and the sixth equation is mxy equals, and when we expand it we find that either in all the terms equal 0. So, this is equal to 0. So, these are the 6 equations. Now, our aim is to find expressions for u naught, v naught and w naught. V naught we have already figured out that its value works out to be exactly 0 throughout the length of the plate. So, for u naught and v naught we consider equations 1. So, when we observe equation 1, it has u naught and w naught, and everything else in the equation is known. A11 is known, B11 is known, nxt we can compute because we know the lamination sequence, and alpha 1 and alpha 2 of the material, and delta t is also known. So, the first equation involves only u naught and w naught, and the fourth equation, the same is true for fourth equation also. So, essentially what we will do is we will integrate these equations with respect to x once. So, we will get an expression in u and dw over dx, and then solve for u naught and dw dx. So, we get from 1 we get u naught x is equal to b11 over a11 dw naught over dx plus nxt hat times delta t times x, because I have integrated it once, and then I get an integration constant. So, that is C5 over A11. Okay. The other thing is, so from likewise from 4 we get another expression for u naught, and that gives us d11 dw naught over dx. Oh, so there should be, I am sorry, there should be here also a11, and from the fourth equation what we get is d11 times dw over dx plus, this is the equation we are considering. So, mxt delta t mxt hat times delta t times x plus another integration constant C7, and this entire thing gets multiplied by 1 over B11. Okay. So, this is equation 7 and this is equation 8. Now, consider the case that if delta t is 0, if delta t is 0, then the plate should not exhibit any u naught. if delta T, if temperature is 0, the only reason plate's configuration is going to change, it is free, it has not seen any external forces. So, the only reason plate is going to change its configuration and exhibit UV and W is because of temperature difference. So, in case delta T is 0, then U naught should be 0, also the plate should not exhibit any curvature. So, dW naught over dx should be 0. So, essentially what I am trying to say is that this thing will be 0, this term will be 0, and because delta T is 0, this should be 0. So, the and which implies that C5 again represents rigid body motion and we can set it as 0. So, we set this as 0. Similarly, we look at equation 4 and we see that, and we again do the same thought experiment, that when delta T is 0, U naught should be 0, dW over dx should be 0. So, and the only non-zero term left is C7. So, for this equation to be satisfied, this also has to be set to 0, because C7 and C7 and C5 represent rigid body translation of the plate. So, once we set these to be 0, what we see is that these modified equations after they are set to be 0 are equations in U naught and dW over dx. So, we have two equations in U naught x and dW naught over dx. These are simultaneous equations. So, we can solve for U naught and dW over dx. So, we solve for U naught x and dW naught over dx. So, when we solve for this is what we get, U naught x equals B11 over A11 script D11 times B11 n x hat T over A11 minus mx T hat, this entire thing multiplied by delta T x, and dW over dx works out to be 1 over D11 times so that's times delta T times x. So, that is the slope of the plate at any given point. So, I integrate. So, this is one important equation, and this is the equation. The next equation is for slope, and if I integrate this equation for slope, that is dW dx, I get W naught as a function of x is equal to this entire expression times delta T times x square over 2 plus another integration constant C8. So, once again, how do we find out the value of C8? C8, we once again think of a scenario that when delta T is 0, then the plane should not bend at all, and that can happen only if C8 is 0. So, this is 0, okay, and C8 represents rigid body motion of the plate. It does not represent any deformation of the body. So, this is the expression for U naught, then we also have an expression for V naught, and then so V naught x is equal to 0. So, these are the relations. Okay. Now, we will discuss these relations for a couple of minutes and then move on to the next topic. So, consider these and think about a scenario that when delta t is 0, when delta t is 0, what does the equation tell us? When delta t is 0, then all these terms they may not be 0, but if delta t is 0, then all these terms are not 0, but they get multiplied by delta t. So, u naught is 0. So, when there is no temperature change, then there is no u naught, and which makes sense. Similarly, in the same is true for the second case also, because the entire solution is a multiple of delta t. So, that is one thing to understand. Okay. The second thing I would like to state is that suppose the plate was symmetric. Suppose the plate was, so in this case we said that the plate is unsymmetric. So, it is 0, 90, and because of this type of plate, 0, 90, the plate will tend to bend when I heat it. It is like a bimetallic plate. If I glue a piece of aluminum and steel together and I heat it, it will try to bend. It is a bimetallic because different materials have different coefficients of thermal expansion in different directions. So, this kind of plate will bend. Suppose the plate was symmetric, let us say it is 0, 90 symmetric, and then we heat it, then we would not expect the plate to bend, but delta t will be non-zero, but then what will make the plate not bend? The reason in that case will be that when we compute the values of nxt and mxt, these values they will work out to be 0 when we compute these values, because what are the definitions of these things? So, if we compute these things, we will find that these terms will work out to be 0, and once that happens, so what I was saying is that this delta t, as it becomes 0, the plates do not exhibit any deformation. The other thing is what happens when the plate is symmetric and if delta t is non-zero, then what would happen? So, in that case we should look at these relations for u naught and w naught. So, when the plate is symmetric, in both the expressions for u and w, we have in the numerator both the expression for u, the entire displacement function is multiplied by this term B11, and when the plate is symmetric, then B11 will be 0. So, u will be 0. Similarly, when the plate is symmetric, B11 is 0. So, and B11 appears also in the expression for w. So, again w naught will also be 0. So, this again meets our physical requirements, and in this way very methodically and logically we can develop expressions for mid-plane stresses and mid-plane strains and thermal stresses and thermal strains in context of plates which are unsymmetric and if they are treated to temperatures. We can also use the same approach to calculate internal stresses for even symmetric systems when they are subjected to temperatures. So, that is what I wanted to discuss today, and tomorrow we will move on to a different topic and we will start looking at plates which are not necessarily semi-infinite in dimensions. So, we will start approaching plates of those types and then we will see how they can be solved. Thank you very much and have a great day.